There seems to be slight confusion with a scale in trigonometry and physics, particularly when dealing with vector fields. So I'm going to be going over that. So remember in trigonometry, I'm going to make it small because I can't draw straight lines for my life. Um, we have a triangle. So let's denote these arbitrary values x, I mean not x, x, y, and z. So this is length x, this is length y, and this is length z. So what happens if we double x? Now let's double x here. And y and z. Sorry, it's like a drawing here. So what happens here? We only doubled this length. Now it's a completely different triangle. So if this was a 3, 4, 5 triangle, now this is going to be a 6, 4, 5 triangle because this is double. And this is no longer the same triangle. Even if you do, like, let's do a sine function here. Sine of opposite over hypotenuse 4 over 5. Let me pull a calculator out. Luckily, there's one right next to me. We get 53 degrees. Now, if we do it to this triangle, wait, it's not -1. Oh, sorry, the hypotenuse doesn't stay the same as well. It got slightly changed as well, so it can't be z here. So now this becomes a different arbitrary value, and let's denote this f. So now it's f, now it's different. So when you change the scale of one side only, then the entire triangle changes. So how do we remedy the situation? Now let's go back to the original example, x, y, and z. Or I should have used x, y, and r because of polar coordinates. But anyways, what happens if you times 2 right here? Now on every single side, so we have 2x, 2y, and 2z. If you do the ratios, you still get the same exact angles. This angle is the same as this angle is the same as that angle, and that is just a property of triangles because they share the same angles, angle, congruence, or angle, similarities. Not side, similarities, but angle, similarities. So pretty much, regardless of the length of the triangles, if the ratios are the same, then it's the same triangle. So what do I mean by ratios? So let's denote this as theta. If sine theta opposite over sine theta, which is opposite over hypotenuse, is the same as the sine theta for this one, which is 2i over 2z, because opposites over hypotenuse, and they give the same answer, then these are the same triangles. This one is just scaled up by a factor of 2. So how can we use scales here? And this is kind of what we get into in my physics class. So let's say someone pushes a cart. They push it with the force of 3,000 newtons. So pretty fast. I mean, if you know Newton's law of force, then you can probably calculate that. But that's a decent amount of force. And then let's say we push something up here with a force of 500 newtons. This is also not to scale because this should be 6 times longer, but it looks like it's only 2 times longer. So this is just an arbitrary triangle. So it's not drawn to scale. So if we calculate the hypotenuse here, and everyone knows the hypotenuse formula, it's a squared plus b squared equals c squared, and then you just square root both sides. Or you square both sides. And then 3,000 squared. You get 3041. So now we have a 3041 vector going this way. But my teacher wanted us to do it instead of using complements or the x and y. He simply gave us the vector and its direction. So what actually happens here? Now let's do some math. On your ruler, there's typically only going to be 12 ticks. 12 inches, or let me do the math, 30.48 centimeters. So you'll typically be given 30.48 centimeters or 12 inches on a typical ruler. Actually, you will be given that. So Unfortunately, if we set 1 Newton equal to 1 centimeter here, and we have a ruler, we don't have 3,000 centimeters to draw out. So we can't draw out 3,000 newtons if we assign 1 newton to a ratio of 1 centimeter. So we can't do 3,000 ticks. But here's what we can do. We can scale the triangle down because the relationships stay the same. So what we're going to do is we're going to divide each side by 1,000. And remember, when we went back to the trigonometry earlier in this video, if you divide or multiply the factors or the sides, it's the same exact triangle as long as you do it to all sides. So let's divide it by 1,000 each. And what we'll get is, we'll get 3, 500 divided by 1,000 is 0.5, and then 3.041. Guess what? We can draw this with a ruler now. So now, if we drew this with the ruler, and let's say we have a ruler right here, and we drew 3 centimeter marks, so let's say this is the 3rd centimeter mark, then this would be how big the x-axis is. Then we take our other ruler, come here, and find 0.5. Let's assume that's like the 0.5 mark. Actually, let's make it a little bit bigger. Let's assume that's the 0.5 mark. And then we can take a 3rd ruler and measure the length of this, which is the hypotenuse. But note that the hypotenuse is also 1/1000 times smaller. So the actual ratio becomes 1/1000 of x, or the length of the hypotenuse is equal to 3.041. Because this hypotenuse is 1,000 times smaller, so the hypotenuse, which is 1,000 times smaller, is equal to 3.041 times 1,000 on both sides, giving us x equals 3,041 newtons. So that is the logic of using angles and a scale. So let's try one more example here. And this time we'll do arbitrary triangles again, just to make it slightly easier. So let's say we have... Let's say we push here with the force of x, y, pretty simple. Now let's say that the x is, well, let's not use arbitrary, let me just use a real world example, 5 centimeters, or 5 newtons. Actually, we have to make it kind of big so we can scale. 50 newtons and 40 newtons. Now, the hypotenuse is always going to be a constant ratio, so that means opposite over hypotenuse is going to be the same regardless of the length of these sides, as long as they maintain the same ratio. So even if it's 5 and 4, which is this triangle divided by 10, the hypotenuse will always have the same relationship, and that is kind of what the trigonometric ratios are for. So this side, 40 divided by that side, will always be the same as the same angle, or the same sides divided by each other. So the opposite over adjacent side will always be the same if it's a similar triangle. So regardless of whether this is 20 and 25, that's just times 5 on both sides, it's always going to be the same because they're similar triangles. So that means the hypotenuse is also always going to have the same ratio, just scaled down. Here we scaled it down by a factor of 10. So now what we're going to do is, on a ruler we can count out 5 centimeters. So let's assume that's 5 right there. And then we can do 4 up here. So we'll assume that's 1, 2, 3, 4. And then you can use your ruler to measure this. And since this will give you a hypotenuse that is technically 10 times smaller than what it actually is, because we scaled all the sides down by 10, we can times it by 10 to get the actual answer, and that is what the point of the scale is. You can assign any value. In fact, I could do 20 here, so that would become 2.5, and that would become 2, yet the hypotenuse always stays the same. To prove it, let's test it out. 2 squared plus 2.5 squared, Pythagorean theorem applied. 2.5 squared plus 2 squared is equal to 3.2. 3.2. Then let's times it back by our scale. So remember, this is 1/20th of our original size. So we times it by 20 to get rid of that scale. And we'll get a thing of 64.03. So the hypotenuse or magnitude will be 64.03. And 64.03 divided by, let's just take the adjacent side here, which is 50. So that would be hypotenuse over adjacent. gives us 1.28. So that means the hypotenuse is 1.28 times bigger than this x value, and the same triangle, just smaller, 3.2 divided by 2.5, also gives us 1.28. And that is the beauty of a scale. The triangles will always yield the same ratios. This side, one side will always be, one side will always be that much bigger than this side, regardless of how long the triangle sides actually are. So if these triangles are the same, then this side will always be the same amount bigger than this side, regardless of the size of the triangle. And that's the beauty of trigonometric ratios and vector fields.